Let's look at some definite integrals. The first integral is similar to an antiderivative we've done earlier, but I thought it would be nice to just see how the fundamental theorem works with some of our new integral formulas. So for the first one, we basically have the integrand of 1 plus log x squared divided by x. So that's another power rule. So again, we write it in a suggestive form. That is, we pull the 1 over x over to the right, and we have the 1 plus ln of x squared. Now clearly the derivative of 1 plus ln of x, we've seen this before, is 1 over x, so no adjustment is necessary. We have the power of u du. So that's add 1 divided by the new power. So we have a new power of 3 divided by 3, 1 plus ln of x to the third power divided by 3, evaluated between e and 1, where this is the base e, the Euler e. And so we just substitute. So we have 1/3, so we have 1 plus ln of e, quantity cubed, minus 1 plus ln of 1, quantity cubed. Now, of course, ln of e, back in college algebra, that's just 1. So 1 plus 1, we get 2 cubed. And of course, ln of 1 is 0, so we just get 1 cubed. So we get 1/3 times 8 minus 1, which is 7/3. So that's a very simple integral, but again, nice to see how it works with the limits and the definite integral. Okay, now this next problem is actually written up in your notes, but I did it differently. And since we showed that there's an alternate form for the antiderivative of the cosecant, I thought I'd change it up a little. In that problem, I actually changed the limits, and here what I'm going to do is do what I've been doing, not change the limits, and use that alternate form and show you that you do get the same answer. The only thing is that you have to be flexible. If you use a different formula, you'll get an equivalent answer if you've done it correctly, but you may have to adjust it to show that they're actually the same. So here we have the definite integral of 8 times cosecant 2 theta minus 8 cotangent 2 theta, evaluated from pi over 8 to pi over 4. So what I've done here first is to adjust it. We just go ahead and factor the 8, and notice that with this 2 theta, with the chain rule, we need a 2 in the d theta. We don't have that, so to get the appropriate du, we put in the 2 and of course pay for it. So that gives us a 4 outside, and now we're table ready. We know the antiderivative of cosecant, and we know the antiderivative of cotangent. Okay, so I'm using that alternate form which I proved. That is the natural log of cosecant 2 theta minus cotangent 2 theta. And then of course the antiderivative of the cotangent is the natural log of sine 2 theta. Now, all we have to do is apply the limits. So we will do pi over 4 first. So when we hit it with a 2, we get cosecant of pi over 2 minus cotangent of pi over 2. That's the argument of the log. And I've noted here cosecant of pi over 2 is 1 and cotangent of pi over 2 is 0. And then, of course, for the second term, we just have sine of pi over 2, which we know to be 1. So that's not going to give us a whole lot, clearly. So let's go ahead and look at the lower limit, pi over 8. So we have minus, so we have natural log, hit everything with a 2, so we have cosecant of pi over 4 minus cotangent of pi over 4 inside the argument of the log. And of course, just to remind you, the cosecant of pi over 4 is root 2, and the cotangent of pi over 4 is 1. And then, of course, here in the second term, we have the minus ln of sine of pi over 4, and of course sine of pi over 4 is 1 over root 2. That's our friend. Now, what I've written here, I just went ahead and elaborated a little bit. We have ln of 1 right here. That is, the argument just reduces to 1, and that's just a 1. So ln of 1 minus ln of 1, that's just going to be 0. That's not going to give us anything. And then as we work over here, we have the argument is square root of 2 minus a 1. So we have, in this particular case, minus the natural log of the square root of 2 minus 1. And of course, I wrote this term second because it has the minus. The minus minus here adds, so I have the natural log of 1 over root 2. So again, just be aware that since we've used a different integral formula, the answer looks a little bit different. So now I've got a minus sign instead of a plus like I had in the notes. So I'm going to use the quotient rule here. So this gives us the 4, and then we have ln of 1 over root 2 divided by root 2 minus 1. Now, when you look at this, if you just bring the root 2 downstairs, you get root 2 times root 2, which is 2. And then, of course, root 2 times the negative 1 is negative root 2. Now, I did a little side calculation here. I took the argument of 1 over 2 minus root 2 and conjugated. So just multiply and divide by 2 plus root 2. And when you do that, you'll get your 2 plus root 2. And, of course, the difference of squares will give you 4 minus 2 downstairs. And so now when you divide, you get the 1 and then the root 2 over 2, which is 1 over root 2. So you get equivalently 4 times the natural log of 1 plus 1 over root 2. Now this was the answer that I got in your notes, and I wanted to show you that regardless of the integral formula that you use, as long as it's legitimate, you will get an equivalent answer. So be sure to make a point to go through these new antiderivative forms, practicing your basic trigonometry and practicing your use of the fundamental theorem of calculus. And we are done.